Another type of gate implements OR logical function, and you should be able to recognize that we have an inverter over here, and we have a NOR gate on this side. So a combination of a NOR gate and the inverter produce the desired OR gate behavior. So in this case, if you take a look at the truth table that corresponds to this type of logical gate, you can recognize the outcome here in the at the output terminal is the implementation of an OR function. When we have 0, 0, 0, 1, 1, 0, and 1, 1 inputs, it produces these outputs which precisely correspond to the behavior on OR gate. Next example of a gate is an AND gate, and you can see that now we're making transition from one gate to another, and you can see that these are some simple connections to gates of different types of transistors, N types and P types transistors. And again, overall the logic here follows the idea is that at these levels here, 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 we have a higher voltage, and at ground levels we have a lower voltage next to 0, and based on the switches by these transistors, the behavior can be constructed such way that we implement a certain truth table if we consider our inputs to be set to all possibilities 0, 0, 0, 1, 1, 0, and 1, 1, and then we can recognize what kind of outputs will be produced by this combination of transistors with respect to these combinations of inputs connected to their gates, and we can observe that the output will be producing these types of signals. And so we can see that in case when there is at least one of the inputs is 0, there will be a 0 result in this output right here. And only when both of the inputs are set to 1, we're going to get the result 1 right here. So only when both of these signals are set to 1 in the input, we're going to get this output. So this becomes quite a routine examination of these gates, and you can see that just a certain combination of transistor connections of their sources, drains, and gates. The gates, notice, are connected to our inputs. Sometimes they're reversed when you can see the bubble in the diagram, and we get the specific behavior. We're not going to stay at the level of transistor circuitry for very long. Generally speaking, we would like to sort of encapsulate these types of circuits which implement popular logic gates by presenting them simply as a symbol. I already showed you that the inverter, when we have a wire, we will be using a bubble symbol to indicate an inverter. But in our digital logic laboratory, sometimes we will be using this kind of symbol, so basically which includes the triangular shape indicating the direction of the circuitry flow, that this would be an input side and this will be the output side, and you can see the bubble is still present here in this diagram. And so these are the symbols to remember: an AND gate, an OR gate, NAND gate, which is a negated AND gate, and NOR gate, which is a negated OR gate. So simply this is an OR gate which inverts the result of an OR logical function, and this is the AND gate that reverses or inverts the result of an AND logical function.